we're going to talk about logistic equations. It is another form of applying differential equations. The form of it is kind of interesting. It's not always given to us. It might not say directly proportion or something like that. So you do have to memorize these two forms in order to do logistic equations. So in this form, this is telling you that this is what the differential equation stands for. This is how the rate changed. The rate of dp over dt is kp times 1 minus p over L. And I'll explain what all of those letters are. If you solve this differential equation, this is the form of the differential equation you would get. To solve the differential equation, it's kind of complicated. It does involve partial fractions, which is not something we've done yet, although we will get there. There is another video on YouTube related to logistic equations where I do explain how to go from here to here. You do not need to do this every time. As long as you know this equation and you know this equation, you can use the two equations together and not have to solve them every time. So it's important to memorize these. The important part here is that L is the limit, and sometimes it's called the carrying capacity. With logistic equations, we're going to be talking about viruses or things that are spreading. And when you start trying to figure out how many people have been affected by a certain virus or things like that, you can only affect the amount of people that are there. And that amount of people or that amount of things or bacteria or whatever it is that we're talking about is L. Okay, and so L is that carrying capacity. That's what L is, the limit. And so that's important. P stands for the population. Most of the time these problems are dealing with the population. K is another constant that you will solve for, and B is also a constant that you will solve for. T is still time. So if we look at the graph of a logistic equation, it's going to look something like this. And as far as this graph goes, notice that up here is the L, because that's the maximum it's going to get. This is P and T, if you think of X and Y. Another important part is here in the middle, and this is at L over 2. L over 2 represents the maximum, or it represents when the growth is a maximum. Like it's going up the fastest right there in the middle. So if we're talking about a virus or bacteria or something like that, we're talking about the time that the thing increases fastest. And it increases fastest at the population of L over 2. Here is an equation of a logistic equation where some numbers are filled in. And so here's some things that we're going to be trying to find. The first thing says that it wants us to find the carrying capacity. Notice this is already in the correct form. Go back to that differential equation. It has to say Kp times 1 minus P over L. P here is Y. There has to be a 1 right there. If there's not a 1 right there, then you're not completely finished. So what that tells me is that the carrying capacity is 50. Because there's already a 50 down there, I know that that's the limit, that's the L. The K is the number in front of the Y, so I know that K is 2. Next thing it asks me to do is write the logistic equation. So all I'm doing is I'm plugging in the numbers that I have based on the information given. So instead of writing P, I'm going to write Y. So Y equals L over 1 plus B e to the negative k t. Now, to finish this problem, I would have to know some more things. I would have to know another time and population, or time and whatever y represented, in order to find b. And once you can do that, then you can finish. But this is the logistic equation that we have based on the information given. The next part said find y when the growth is the greatest. All right, I know that the growth is the greatest when the carrying capacity is 50. So y would be the greatest, or the growth is the greatest when y is half of 50. So this would be 25. Here's another example of a differential equation. Notice that this example is not already solved for dp dt like it should be. I don't see a 1 there. So what I need to do first is I need to factor out what's in common because I want a 1 at the beginning. And what I'm going to factor out is 2/3 y. Because I know I'm supposed to have a number and a y at the beginning, so that's what I'm going to factor out. That will give me my 1 that I want right there. And then I know that that will give me a y, but the rest of it I'm not sure about. So I'm factoring out a 2/3. And so what that means is I'll have a 1 over 300. I'm going to take 1 over 300, and I'm going to divide it by 2/3. And then I'm going to change it to a fraction. That gives me 1 over 200, so that means that I have y over 200 right there. Now, this actually is, all I've done is I've rewritten dy dt. So now I can answer my questions. My carrying capacity I know is 200 because that's the number underneath y. My k is the 2/3. And now because I rewrote that, because I know the carrying capacity in k, I can write down my logistic equation, which is 200 over 1 plus b e to the negative 2/3 t. Now, if I want to find y when the growth is the greatest, I know it's growing the greatest when the carrying capacity is half of what it really is. So I know that y is going to be 100 because that's 200 divided by 2, and that's when the growth is the greatest. That's when it's increasing the greatest. Okay, so here's 2 examples where, if you'll notice, it's already solved for P. It's already logistic, and similar kinds of questions, but we already know some of this information because it's already solved for P. So A says to find the carrying capacity. So carrying capacity is the limit. Notice both of these equations are already solved for the limit. So for A in number 3, it would be 1,000. For B in number, or A, sorry, in number 4, it would be 3,500. Because L is just the number on the top. K is the number with the power of E. So it's 0.2. It's not negative because negative is just part of the equation. So in number 4, it's negative 0.01. I told you negative, it's supposed to be positive. K is always the positive value because when you plug it in, it becomes negative. All right, the initial population is when t equals 0. So in C, for number 3, I'm going to plug a 0 in right here for t. That will give me 1. And so it's going to be 1,000 over 31. And I get approximately 32. So the initial population in C, it would be 3,500 over 1 plus, you're plugging in a 0 for t, so 1 plus 5, which is 6. And you get approximately 583.3. Most of the problems you'll have, these will come out to normal numbers and not decimals because we're talking about a population. But in this case, this is what we get. So D says find P when the growth is the greatest. Remember that the growth is the greatest at the carrying capacity over 2. So I know that for D, that I should get that divided by 2, so I get 500. For D here, I get 3,500 divided by 2, which is 1,750. Okay, lastly, we're going to look at a word problem related to logistic equations. Normally, the problem would tell you this situation is modeled logistically. So if you see the word logistically, you know that you have those equations to memorize and use. So the first thing that it wants us to find is the differential equation, then it wants the logistic equation. So let's start off. It says at t equals 0, there's 5 grams of bacteria. 1 hour later, there's 8 grams, and the maximum weight is 30 grams. So we want to start off with trying to figure out the logistic equation because the problem doesn't say the rate changes at this rate. If it would have said that, then you might be able to write the differential equation. We're going to go backwards. We're going to start with logistic. So we're talking about bacteria, so I'm going to call it B. You can call it whatever you wanted to. We know that the maximum weight is 30, so that is L. All right. in our equation, we know that it's supposed to be 1 plus b e to the negative kt. Okay, and we're going to use information from this to find k and then to find b. Okay, so up here at the top, kind of like we've done before, we're going to make a little t-chart. We know that 0, 5 is how many we start with. We know that 1 hour later it's 8. Because it says hours, I'm going to go ahead and use hours. And so that's the 2 points that I'm going to use originally to find everything that I need to find. So let's start off with the 0, 5. So 5 is going to equal 30 over 1 plus b e to the 0. From there, I would probably cross multiply and get 5 times 1 plus b equals 30. Divide, you get 1 plus b equals 6. And so that means b is 5. Next, you're going to figure out what k is using the 8 and the 1. So 8 equals 30 over, we already know b is 5, e to the negative 1k. Again, I would cross multiply. 8 times 1 plus 5e to the negative k. Okay. At this point, I'm going to do some calculator work, but I'm going to talk you through it as I go. We're going to take 30 and divide by 8. Then we're going to subtract 1. Then we're going to divide by 5. At this point, we have e to the negative k equals 0.55. I'll write that down. You're going to take the natural log on both sides. And then if you divide by negative 1, you'll get that k is 0.597. So now I know b and I know k. So to write my real logistic equation, we're going to fill in everything we know. b is 5 and e to the negative k. So change that back to negative and then put your t. When we do the rest of this problem, you will be using that whole value of k in your calculator, so keep it there. Alright, because I have this equation, that means I can go back and write the differential equation just using the letters I know. So db dt equals, it starts off with k, so that's 0.597. And then b, 1 minus b stays in the equation, over L is 30, and so that would have been the differential equation to fill that in. Alright, next part says find the weight after 6 hours. Well, all that means is I'm going to put 6 in the place of t. So I'm going to do 30 divided by 1 plus 5 e to the negative value. It's already negative in my calculator, so I'm just going to copy it down and not put another negative. And then I'm going to times that power by 6. And so I get 26.35, and it asks for the weight, and so that's grams. Alright, next it says, when will the culture reach 15 grams? Well, that's whenever you have 15 equals 30 over 1 plus 5 e to the negative 0.597 t. And you're trying to solve for t here. And it's similar to how we solved this here. You're going to cross multiply. And then again, I'm going to do the calculator work. 30 divided by 15. Subtract 1. Divide by 5. Take the natural log on both sides. And divide by that k value that is still in your calculator. And we wanted to know when it would reach 15 grams, so you're coming out with a time, and I ended up with a time of 2.692. Lastly, what is the weight when the bacteria increases most rapidly? I know that the bacteria increases most rapidly when you take the carrying capacity and divide by 2. We know that the carrying capacity, or the limit, is 30.